So we're looking at pair distribution functions through both X-ray diffraction as well as neutron diffraction. So I'm Al.
I'm Brian.
I'm Yadu.
And AJ is currently with us in reciprocal space. So just starting off, what PDFs are. So when we look at pair distribution functions, our goal is considering a bulk model of atoms and trying to figure out how atom-atom positions are related. So what we're effectively doing is pick a given atom and let's look at what distance atoms are around it. So in the case of a nickel in an FCC lattice, you'll get at about 2 and a bit angstroms. You'll get all its nearest neighbors that'll line up right at the certain peak. And then as you go further away, you get another set of atoms that pop up, and so on and so forth, where you get this nice, pretty lattice structure. And more specifically, we can break down PDFs into a bunch of different subcategories based on what we're looking at. So in pair distribution functions, what we're looking at is we scale out this probability of finding atoms with respect to a random distribution, where it's normalized about 0. So as we see, we start off with this downward slope, which gives us information about the density of the system we're looking at. And based on how these nearest neighbor peaks oscillate, once this terminates to 0 in the case of a nanoparticle, we can actually get information about the finite size. And with specifically pair distribution functions, we can also see that by scaling with distance with our function, we can accentuate some of the long-range order that may exist. A more basic rudimentary way to look at it is through a pair correlation function, which is a purely normalized histogram with respect to a random distribution. So when we have no atoms at a certain distance, we get 0 intensity because there's always, in the case of a random sample, there's always some non-zero probability of finding an atom. When we go above 1, that means we're in a situation where we're more likely to find atoms in this model than we would in a random model. And so once we eventually terminate at 1, that means we've lost all long-range order and we are now equivalent to some random ordering. The other variation that's commonly used is a radial distribution function, which, like a pair correlation function, is a histogram, except now we're no longer normalized to the possibility of a random distribution. So as we go further out into space, we'll find more and more atoms because we're probing a larger surface area where atoms can appear. So we still have this nearest neighbor regime here, but now these next nearest neighbors become a lot less resolved. So, and from there, we can start considering more interesting systems where we have different atoms and elements. So in the case of water, we have 3 different situations that can happen. The first is we can look at the correlations between oxygen-oxygen bonding, and they'll have their intrinsic bond distances. We'll also have oxygen-hydrogen / hydrogen-oxygen, and those will have their own intrinsic positions where you will have peaks where you'll have these bonds and areas where you don't. And finally, you have hydrogen-hydrogen. And when you combine all these together, you get this total pair distribution function. Although these little breakdowns are usually what's interesting when you're trying to analyze a structure or look into what's going on in your system. So we have a few different ways we can try to probe this. And the best way to do it is using either neutrons or X-rays. With X-rays, we have the options of either going to a synchrotron like APS, or if you're very fortunate, you can be doing it in-house in your own little fancy diffractometer. Of course, what we want to do is, in order to get all this spatial information, because we're diffracting, we need to go very far out into Q space. So the downside of using lab X-ray sources, where you have something usually like a copper anode, so you have an 8 keV X-ray beam, is that you're going to be extremely limited by how far out into Q you can go. However, with synchrotrons, you no longer have that problem, and you also get that big advantage of having all that flux that comes with it. Neutron sources, on the other hand, you don't get that same flux as a synchrotron source. However, where neutrons come in handy is that they scatter off of elements differently than X-rays. And that distinction of how neutrons versus X-rays scatter can give us better information about elements. So one thing we know offhand is water, for example, likes to be scatters really heavily with neutrons, while with things like X-rays, it'll mostly pass through. So if you have a system with a lot of heavy metals and some oxygens, in the case of X-rays, the correlations that you find are going to be extremely weak, and it's going to be very difficult to resolve. If you use neutrons, on the other hand, you can actually pick up a lot of those weaker elements much stronger than some of the heavier elements. And so one of the most common things to do is actually use both these methods in tandem to fully resolve what these element-element correlations are in whatever sample you're looking at. The other advantage of neutrons is that we can do something called isotopic substitution. And the idea of that is, let's just say we were looking, one of the popular things we keep hearing is, if we're looking at something with hydrogen, what happens if we stick deuterium in it? Or in this case, if we can use a different isotope of lithium. And with neutrons, when we switch the isotope, we're going to get a different cross-sectional area, which means that the scattering effects are actually going to be quite different. And so by doing this, we can actually resolve some of these. We can look at the differences in our scattering function, and that can actually give us more information about where the lithium correlations are versus other elements. And on the other hand, X-rays don't see this effect, so we can combine the two to get a whole slew of more information. And since we are dealing with nuclear differences, the overall chemical structure of what you're dealing with isn't going to change, although there's a very weak counterexample with water because the difference between hydrogen and deuterium is subtle and it's slightly noticeable. So when we want to create a PDF, our general process is we want to go and get a large measurement of how our radiation scatters out to high Q. From there, we're going to break that down to get our scattering function and Fourier transform it into that pair distribution function that we saw before. And from there, we can do things like what we saw with the powder diffraction groups, where we can start probing and solving that structure into more details. And then, of course, afterwards, you can get published.
I'm going to talk a little bit about the measurement process here. So now you have the sample, and you have a neutron or X-ray source. What else do you need? You need a detector. So the next important step is choice of a detector. You can either go for a pin diode detector, a pixel array detector, or a silicon detector. So that's the next step. Then what you need to do is you need to calibrate the detector. For that, I'm just going to jump over it. So this is what we use to calibrate the detector. This is cerium oxide calibration sample. This is a known sample, and you know where the peaks are. So this is what we use to calibrate the detector. Now there's another option between us. So we either need a higher Q range or better Q resolution. So if you have a big sample, you need lower angle scattering, and you need better resolution. So that's the next step you have, and that you can determine by increasing the distance from the sample to the detector. If you have higher distance, you have better resolution and lower Q range. Then the quality of the sample, as you know, and then you should have the ability to remove all the background. So this is the process. You have a sample here, and you have the X-ray or the neutron coming from here. It falls onto the detector, and this is the powder diffraction pattern you get. From there, you can directly determine the intensity versus the 2 theta or the Q. Then from there, you can go to the Q space here. Then Fourier transform it to get the PDF, the PDF. And this is a typical crystal, single crystal pattern. And so we can also look for powder diffraction. In that case, it will be rings instead of different dots. This I already mentioned, and so yeah, this is what I mentioned about the different distances. This is 2 nickel samples. One is a distance of 17 centimeters, and the other one is distance of 25 centimeters. And you are able to see the red and the blue peaks, right? So that is a change in resolution you obtain. And
okay, so you've gone to the synchrotron or the SNS, you've collected your data, you've lost a lot of sleep, And now you go back home and you need to do something with all this data that you have. And so this is where all the data processing comes in. And sometimes you'll want to know the chemical composition of the sample that you're using to help you manage the data transformations. You may not want to use all of the Q data you collected. You may get high noise at high Q levels. And you're going to want to mask bad dead pixels or that beam stop that's in the way and interfering with the nice rings that you have. And this is an example of some background subtraction. And so this is a liquid sample, and it's hard to see, but the green line is the sample, and the red line is the blank. And they're pretty much right on top of each other. And so this was collected at 11 IDB. And you don't get as much background when you just have a powder sample, but we can still do the subtraction, and we can still get actual peaks. But it's important that you're collecting a decent background to actually do an accurate subtraction in order to actually get the information for your sample that you're looking at. You guys saw this already, but just again, this would be maybe the background subtraction for a powder sample where it's just the kapton instead of the liquid, some sort of a water background as well interfering in your scattering. And then you transform it, or you get the Q space, your structure factor, S of Q. Sometimes you'll also see F of Qs, which is the structure factor multiplied by a factor of Q, which helps bring out some of these lower features that tend to die out, and it enunciates them. And then you do your Fourier transform, and you get your G of R, which has your real space. Every peak is an interatomic distance in between two atoms.
Okay, and then once you've collected your data, you have to go and solve your structure. So when you're solving it, you just want to make sure that when you're generating your PDF patterns that you kind of do it the same way, just so when you compare it, basically you're not comparing apples to oranges. You want to check for artifacts and then finally refine it. And so this first example actually comes from an alumni of the NXS school, Joshua Greenfield, who's in my lab. And so he was looking at this beta iron selenide, which garnered a lot of attention when it was discovered to have a superconducting transition at 8 Kelvin. And so people are excited about it and looking at it as like a parent material for studying like structure property relationships. And so most people were doing high temperature synthesis, which inherently has a lot of shortcomings. So his idea was to synthesize this using lower temperature solvothermal methods. And so what he ended up finding is that he had a lot of variability from synthesis to synthesis. So these bottom two samples, this is the electrical resistivity, you see a superconducting drop. Whereas some of his samples wouldn't show that. And so he took these samples to Nomad here at Oak Ridge. And so up here, we see part of the PDF pattern. And so you can't really see it too well, but there's two lines under the blue one. So these correspond to the superconducting samples, and then the red one corresponds to the one that didn't. And so after refining these patterns with some hard work and some tears, he actually found out that a lot of these extra peaks corresponded to either iron-oxygen or iron-selenium distances. So basically, he couldn't see this in lab powder diffraction. And so then he eventually took his samples to 11 BM and was able to see some very minute peak shifting. And then so you can also compare samples. So these are 3 different compounds that have calcium, phosphorus, and oxygen in it. And so you can see down at this lower radius, a lot of the peak positions are very similar. So these correspond to, say, like phosphorus oxygen distances or calcium oxygen distances. And so the local structure is very similar, even if each of the 3 have very different crystal structures or amorphous structures. And then as you go to farther and farther radii, you see that the patterns don't look anything alike, because as you go farther away, they're just very different. And the amorphous sample just loses all definition. And so there are a lot of useful programs and tools that you could use to analyze PDF data. Some are better than others, like some are better for amorphous samples and some are better for crystalline samples, and so you just kind of have to figure out which is the best for your data.
And that pretty much wraps it up. So we've gone through how to get your PDF, and all that's really left is to take your structure and get it published, which we'll leave for you guys. Thanks. So usually your G of R will become a lot more broad with higher temperatures because that thermal vibration is going to lead to this ensemble average of atom-atom distances being closer or further apart based on that vibration. So you'll have a much more broader peaks.
So can you extract atomic displacement parameters or mean atomic displacement parameters for the sample?
You should be able to, provided that you have a good set of measurements at other temperatures as well to kind of isolate those variables out. One of the big tricks and challenge hurdles with PDF measurements is that you have to have very good control over how you generate your PDF because there's a lot of ways and a lot of quick ways that any slight differences can compound in that Fourier transform and convolute your data. So as long as you have those kind of all sorted out and controlled, you could be able to extract that. Yep.
So you just used the total scattering, right? You didn't try to separate out coherent, incoherent, or elastic, inelastic, or anything like that, right? I mean, so is that useful, or do you just ignore it for most purposes?
So it can be important, especially depending on how much detail you want to go in. So in our case, the amount of Q space that we went into for some of our examples wasn't high enough where a lot of the incoherent effects will dominate. There are some cases, and I have, at least within our group, where we actually we also had energy sensitive measurements to actually probe out and factor out some of that inelastic and Compton scattering to filter it out of our scattering functions before we solve out the PDF. But most of the time from what we've seen, the effects are fairly small, and usually any subtleties that'll come into it are overshadowed by noise and just other factors that are a pain to remove. Yep.
Was the comment that typically use a vanadium can, which is it scatters incoherent?
Oh yeah. So yeah, that's so in the case of, for vanadium, in the case of neutron scattering, you'll usually use something like vanadium as your calibration for your detectors, and it'll also give you a good background because it's all incoherent scattering. So you get that, when I was talking about that almost comparison with your G of R with a random scatter, that's almost your perfect candidate as your random atom placement.